Okay, so our next speaker is Bart Oldman, and he's going to tell us about their setup at Compute Canada. Welcome.
Thank you. So welcome everybody. My name is Bart Oldman, and I work as an HPC analyst at McGill HPC Center from McGill University, which is collaborating inside Canada and Calcul, Quebec, and then Compute Canada is basically the collaboration of all academic supercomputers in Canada. So what I'm going to present is how do we deal with software on our supercomputers. And we combine various technologies, software solutions that have been covered already before, particularly in Kenneth's talk. They're all open source, so it fits really well in FOSDEM. All these four things, CVMFS, NIX, Lmod, and EasyBuild, are all present on GitHub, actually. So what we're going to in Canada is a bit of an upheaval of our supercomputer infrastructure. That's kind of the motivation, that we're moving from a system where pretty much every research university had their own little compute cluster, and some had bigger ones, to a more national setup where there are basically 4 bigger systems and one cloud system. And the 4 bigger systems: Simon Fraser University, Cedar, University of Waterloo in Ontario with Graham, Niagara at University of Toronto, and a new system in Quebec, which is called Beluga. So just to give you an idea of the scale of the system, the Cedar system in Vancouver has about 900 compute nodes, going to be extended soon with 625 nodes, and also about 500 GPUs. So that together gives about 30,000 total compute cores to work with. The Graham cluster is quite similar. It has a few more compute cores, but fewer GPUs, about 35,000. And the new system in Toronto will have 60,000 cores. So these are, in the HPC world, they're not top systems in terms of the top 500. You won't find these in the top 10, but you will find these in the top 100 or somewhere. So what we're trying to present to our users is, when they log into one of these new clusters, they see a similar software environment. And because many of these new systems are actually pretty much every supercomputer in the world is running Linux by now. So you think, okay, well, they're all running Linux, so they get a similar interface. Well, in practice, that's not the case. Whenever you go to another supercomputer, you'll find that there are very many minor differences in how to operate them. They're not very portable between each other. So we're trying to avoid that by distributing the software that's used on our clusters, and combining 4 different solutions. One is a distributed file system called CVMFS. One is a package manager called NIX to try to have some base software setup that's independent of the underlying Linux distribution. And then we have EasyBuild to install scientific packages. And then there's something called a module tool, Lmod, so I'll get to in a minute. So the background is really, if you log into an HPC cluster, you will find that it runs typically in almost all cases, an enterprise Linux distribution. And in most cases, that's either CentOS or Red Hat Enterprise. Sometimes you may see a SUSE cluster, even rarer is an Ubuntu cluster, but they typically don't run Fedora. And one of the troubles with that is that they tend to be relative dinosaurs. Well, in the open source world, there are very many clusters who run Red Hat 6, which has a 2.6 Linux kernel, GC 4.4, glibc 2.12, Python 2.6. So that is really, like, you think, I'm going in a time machine, I'm going 10 years back. But that's just the way they work. It's mostly for vendor support. Vendors will say, I have a driver for this particular system, and they typically include all the enterprise distributions. And also Fedora has two new releases a year. You don't want to upgrade your OS on the cluster twice a year. It's just way too much work. So nowadays, production clusters of a couple years old, they tend to have 6. The newer ones tend to have 7. But users, some of which may run Linux at home or at their office, want something newer, and they may run Fedora 27 or some Ubuntu or you name it. So they read instructions. They try to run their software, which is not included as an RPM or whatever in the underlying Linux distribution, and they read the documentation. And documentation has a little section about Linux. They go to that section, and the section says, oh, if you want to run it on Linux, it's simple. Just do sudo apt-get install Python 2.7 dev to get Python 2.7. Because as I mentioned, Python 2.7 not installed by default on Red Hat Enterprise 6. So they try to do that command. They get a little lecture about sudo. We trust you have received the usual lecture, etc. It boils down to 3 things. And then it asks them for the password. Well, they have a password, so they type the password. And then it said apt-get command not found. Why is apt-get not there? Oh, I'm running Red Hat. This is not Ubuntu. Okay, but Red Hat has yum installed, so I'll try yum install. Oh, okay, so sorry, user gsmith is not allowed to execute this. Sometimes they get sometimes they get something meaner. They say, you're not allowed to do this. This incident will be reported. It depends on the version of sudo. I don't know which one does what. So they send us an email. Either they say, can I please have root access on your cluster? Or they say, I'm so sorry for typing sudo. Now this incident will be reported. Please don't report me to the FBI and the CIA. So what we do to alleviate this problem is modules. So what does a module do? So what we do is we install many commonly used software packages in a location somewhere on the shared file system, which is not in /user/bin or some other OS controlled location. And we call that a module file. And these module files have been around for a good 20 years or so. And you'll find them on pretty much any HPC cluster. So what you do, this is the old TCL module file syntax, is that you write a little file that you put in a central location, and you specify where is the root of where I installed the software, like the prefix that I used to do configure. And in this case, this is for Python 2.7.9. This is an existing module for our old system. And then you put a few guidelines in that module file, and then the module command, which is called module load Python /279, will modify these 4 environment variables, men path, LD library path, and C path, so that once they load the module, they can execute that software by just typing Python, and they get Python 2.7.9 instead of Python 2.6.6. Same for C path and LD library path. This way they can link to development libraries from Python. Nice thing about modules, modules can be unloaded, so then the module unload will say, hey, oh yeah, the Python module has added these paths, so now I unload, so it will be removed from the path, and I'm back to my original situation. Because of multiple versions, you have Python 3.6.2 installed as well this way, and then you can do module load Python 3.6.2, and it will take precedence over the other Python. So the thing with modules, how they got installed in the past mostly is by hand. And this gives some advantages. As you can see on the right, this is some idea I got from Kenneth. This is a nice little comic strip. And Kenneth got with us up, and other people at Regent, he wasn't the one who started it, but basically they came up with a solution as to why does every cluster in the world write their own module files and install it by hand. There's a lot of duplicated effort. Let's work together and get an automated solution that basically takes the recipe, installs the software, creates the module file, and you're all set to go. Then you can contribute the recipe back, and others can use that knowledge. However, the problem is then, if you adopt that, you are no longer invaluable, so it may not be the best for your job security. So At Compute Canada, we took that a step further, and we're not only installing a few scientific packages via modules, we basically replaced the whole user stack. So we have the bottom layer. This is basically CentOS 6 or 7, has the OS kernel, daemons, anything that's privileged. We don't touch these. We basically replace anything that's in the user space that is not privileged, so it doesn't get too many security issues either. And we install many base packages like GNU libc, AutoTools, MakeBash, cat, ls, awk, wrap, find, you name it. They're all installed using Nix, the package manager, and then accessed via a specific Nix profile, like some sort of prefix with a symlink forest behind it that we put over here in the CVMFS shared file system location. We have a few custom profiles when there's multiple versions of the same tool that we want to make accessible, and then we have many things installed via EasyBuild. Those are usually scientific applications, high-level applications that depend on MPI that run in parallel. Yeah?
Are you bootstrapping EasyBuild in Nix?
Yeah. Yeah. We have to bootstrap Nix because it has a non-standard prefix. Otherwise, it would start with /Nix. So we cannot use any of the binary cache that Nix provide. We have to do everything from source. So the advantage is then that we can have multiple architectures. Not all of our clusters have the same architecture of optimal performance. We have multiple trees depending on the architecture. So, which is not the case for the Nix layer. All these 3 layers are architecture independent. Well, they're all x86, but we don't have any other clusters, and we don't plan on that either. So the distributed file system is something that comes from CERN, originates from higher energy physics. They have a lot of software to process their collision experiments, which are then treated in data centers around the world. So they're used to distributing software for quite a while already, and they use a distributed file system that works on top of it's a FUSI plugin, so file systems in user space. And it works quite well. It has a lot of redundancy built in for a distribution layer with multiple caches. So the idea is here, we build our software on a build node, then we push it to a central distribution node, which is called the Stratum 0. That in turn replicates it into a set of Stratum 1 nodes, which in Canada we have 2, soon 3 of them, and then they get in turn replicated on the Squid node, which is local to the cluster, and then the client node can mount that file system. And even if some of these Stratum 1s go down, you still have access to your files because of the multiple caching. So what you need basically to mount these systems is a public key, and then once you have the public key, you can mount the file systems, and you can use the software. We have a special restricted repository too with some commercial things that not everybody's allowed to see, and only people have a very specific, what we call LDAP structure, with very specific UID mapping can see. So the other tool is Nix. It was briefly covered in Kenneth's talk at 9 a.m. So this is how we can actually provide a newer user space than what's provided by CentOS. We're actually tracking the September 2016 release. At some point we can upgrade it, but we can upgrade it. It's a control by us instead of whatever Red Hat does. So we have a fairly new glibc and CCC and core util stack, and so people will see all the newest bells and whistles for the most part in the default stack. So that's in the path when people log in. The next tool we use is EasyBuild. This is for the more scientifically oriented modules, and Lmod, which is a module tool, much like I presented earlier, is that we have environment modules, an older solution, and then Lmod is a re-implementation of modules. In Lua, that's why it's called Lmod. Lmod doesn't have a shiny logo, but it comes from TAC, and this Texas Advanced Computing Center. Robert McClay who works there, so I just put the tech logo here. So we use Lmod for the software hierarchy. It's nice because there are multiple implementations of MPI to do parallel programming on a cluster of multiple nodes. And if you don't do a module hierarchy, you get many modules. You get, for instance, a popular parallel package called Chromex. You might have a Chromex for OpenMPI, a Chromex for MVA-Pitch2, a Chromex for Intel MPI, and they all show up in your module listing. So you get a very crowded module listing with one module for every MPI flavor and multiple versions of the MPI flavor. It quickly gets out of hand, so that's why we have this hierarchy. The same for compilers and multiple compiler versions. So if you have, say, 2 different compilers, 3 different compiler versions, and 3 different MPIs, you get to 3 times 3 times 2, 18 different modules for the same software package, and you don't want to have them visible by default. So conceptually, what we do is that we fork some Git repositories ourselves. We have the Nix package for Nix, and then EasyBuild is 3 components: framework, EasyBlocks, and EasyConfigs. The framework is the high-level Python script for EasyBuild. EasyBlocks is basically a Python script that says how do I compile it, and EasyConfigs are recipes that basically say what parameters do I use to compile it, configure parameters, where do I want to put it, just little descriptions. So what we do in our team, we figure out if something should go into Nix or EasyBuild in general. If things are not performance critical and are more base, more boring dependencies, they're typically also provided via RPMs or DEP packages in Linux distributions. We install them via Nix. If it's something that is performance critical or depends on MPI, we put in EasyBuild. Then we build it on the build node using nixenv or EB. It's the utility to install it. We test it there. We have a testing development repository. We test it there, and if everything goes well, we push it to production, and all the users will see it after about 15 minutes. So to get an idea about the difference, there's a gray area between Nix and EasyBuild. EasyBuild is focusing on HPC. Nix is focusing on general software. There's some overlap, and these are all packages that are provided by EasyBuild as recipes, but we found them to be a bit too low level, and typically we don't expose these as modules to the users because like something like package config, we say, okay, it's provided by default, and typically the latest version is okay, and you don't really need to provide multiple versions of package config. There's some things we may want to move, like gnuplot is one where we may want to provide multiple versions. But things like autoconf, automake, yeah, I mean, unfortunately you sometimes need multiple versions of those because of compatibility issues. But even there we can create a module around a specific Nix version. So mostly EasyBuild provide recipes for those because the Red Hat development RPMs were too old, and we work around that by providing modules, but we ourselves work around it by using Nix. Another example of packaging that we do is slightly out of this, is that we provide Python wheels. So often people want to use pip install some package and say, how do we do this? Some people insist on using Anaconda. We also accommodate for that, but this is just the standard Python setup. And in order to get optimized Python packages like NumPy and TensorFlow and things like that, we provide our own wheelhouse so that when people do pip install some package in a virtual environment, the package gets downloaded from this particular wheelhouse instead of going to the World Wide Web and downloading some random binary that may not work so well in our cluster. So some of the statistics. So at the moment, we have a monotonically increasing list of modules that we installed. At the moment, we're about 500 software packages and versions that we make available for users in the scientific domain. And there's many more that have other architectures as well. Sometimes we need to install something from multiple architectures, and we do that mostly automatically. So to see what scientific tools do we install, just to get an idea of the distribution. There's a huge amount of bioinformatics software out there. There's just many, many, many different tools. We install them mostly using EasyBuild. At the moment we have about 145. There's probably another 145 coming. And you'll see that other domains typically have fewer applications that many people use. For instance, in chemistry, molecular dynamics, you have Chromax, you have NAMD, a couple others. We also keep track of module load, so we can say, okay, who's using what software? This is a Grafana interface that basically says, we can see, okay, do people use a certain module, and if they're no longer doing it, maybe it's time to retire that module. Or if we say, okay, maybe that module is too old, is there anybody still using it? Okay, time's up. So we have a couple challenges, mostly related to the non-standard path. If you have any questions, I can let you know, but we do a lot of workarounds for that, including a huge module file, just to make sure that the software really doesn't look /user, and that's basically. The other challenge is to hide the NIC store paths with all their hashes to the users, because if they leak into the user's environment, which may not use NICs themselves, and we do garbage collect, then stuff stops working. So this is the challenge, that we combine NICs with something that is not NICs. So internally, it's all super consistent, but when you combine with something else, you may have funny things happening. So I have a lot of people to thank. My colleagues at Compute Canada, Maxime Boissonneau, who leads the Research Support National Team, some NICs experts that we have, and some of my local colleagues and people who maintain EasyBuild, like people at the University of Ghent, Jülich, and Robert Smith, also in Canada. Thank you.
Thank you. I think we can have one quick question.
Yeah.
What do you use to maintain the Linux installations on the compute nodes?
The Linux installation on the compute nodes, they're typically provisioned. I think we're using Puppet at the moment. Puppet. They used to use XCAT on all the clusters, an IBM solution. So these are typically provisioned. They're all automated. You provide a fixed recipe with a bunch of PostScripts that alter the installation, and so you have an identical installation on those compute nodes. Yeah.
What's your method to determine if users are still using a module?
Well, we basically, if anytime anybody loads a module, it gets logged.
Oh.
We parse the logs. One question out back. Yes, we do. The question is...
Can you please repeat the question?
Yes, the question is, do you have optimized Python packages? Yes, we have a generic wheelhouse, and we have AVX2 optimized wheelhouse, etc. Yeah.
Thank you very much.
Thanks.